Good afternoon, everybody. Yes, it's already big here. My name is Barbara Lothenbach. I work at EMPA. EMPA is the Swiss Material Research Institute. There's a connection, if you use the German name, there's a connection to EMPA. EMPA too. In English, it's impossible. In German, it means Eidgenössische Materialprüf- und Forschungsanstalt, just in case. Basically, on my daily basis, I mostly do thermodynamic modeling. And one of the fields where it's really interesting to apply thermodynamic modeling is actually supplementary cementitious materials. Because most of these supplementary cementitious materials, they are glassy, amorphous stuff, which makes it experimentally very, very challenging to catch them and to understand what's going on. Because you start basically from a material you do not see, you to transform it to something else you do not see. And then, that's more or less the challenge. But maybe just to start with, why are we interested in STMs, so supplementary cementitious materials? I think Karen already explained it quite really nicely this morning. We need a lot of cement. Cement is a great material. It's a great material. Unfortunately, we produce quite a lot of CO2 if we produce it, because of the big quantities. And the problem is we don't produce CO2 just because we have to burn to make clinker, but we also produce a lot of CO2 because of the material. And more specifically, because we have a lot of calcium oxide in the final material. And the calcium oxide, it comes all from this nice limestone deposit, and then we heat it above 1,000 degrees, and then a lot of the CO2 you had originally in the limestone just has to escape. That's chemistry, and there's nothing else you can do. So one option you could do is to reduce the big amount of calcium oxide we have in our general Portland cement. And if you reduce that, then the most easy way is normally use some supplementary cementitious materials. And more importantly, you also change the chemistry. That's where we come in. Because yes, you can replace one thing by the other. If you do it properly, you get the same strength in the end. That's very nice. But if you don't understand what you also change in addition, how you change the chemistry, it would be very difficult to get to new supplementary cementitious materials. What are the traditional STMs we know of? We have limestone. We already spoke a bit about limestone today. I will show additional data on limestone. We have the Portland cement. Yes, I manage now, which is, as you've seen before, is quite calcium rich. We have slag. We have fly ash, which contains already much more silica. And maybe the extreme case would be silica fume, or we can use natural phosphate. So you see, depending on which material we use, we have a big variability of chemistry. I mostly want to speak about four STMs, putting this in parts, about four STMs, about limestone, about slag, about fly ash, and about silica fume. Blast furnace slag is basically a byproduct from the steel production. Normally you let it cool quite fastly, and then you have to grind it, and that's why you have this typical structure. The next one, fly ash, it gives the very beautiful picture you can see here. It's actually nice, very, very, very small balls. They have, if you cut the surface, you see circles. It's again a byproduct of coal combustion, and the main part of this fly ashes is amorphous and reacts if put in contact with cement. The last one I want to speak about is the silica fume. This is a picture I found on the internet. It's actually quite impressive. This is the size of a cement. This is the size of a fly ash. And this is the size of the silica fume. So this material is just very, very fine. It's mainly composed of silica, but because it's so fine, it reacts within a reasonable time. And if we look at it in an even more at the a smaller scale, then we can see it also forms nice little balls. Now, I will try, as Karen said, I will try to give an overview what many people in Nanocem have done, and I start with just putting a list of projects that had some connection to SCMs we did within the last 10 years. Yes, 10th anniversary. So we already seen this morning the project of Thomas Machai, where a lot of thermodynamic data have been measured or remeasured. We also had one on blended cements from where Vanessa was involved, and you will see also some data from this one. And in between, we also had some much more influence of SCM carbonation, influence of SCM on reactivity, on hydration, chemistry, and so on. In addition, we also had this two big Marie Curie projects. The first one on new materials with a focus on durability, and the second one more on water, as you've seen today in the presentation of Peter McDonald. And maybe in the future there will be a third one. We hope for it. In addition to this Marie Curie and Nanocem project, we also had a lot of additional projects. Partners project, we just had a project from the Swiss National Science Foundation. So there's data and knowledge coming in from a number of projects. And maybe I want to put out also this Violent Technical Committee on SCMs, where we just had a meeting last week, and we spoke a lot about this, how to measure the reaction of SCMs. I will start with a very simple example, this example of limestone, which you already have seen today by Thomas. This is thermodynamic calculation, where we investigate what happens if we replace between 0 and 10% of the Portland cement by limestone. And the interesting point is up here, where thermodynamic modeling predicts we have somewhere a maximum. Now, why do we have this maximum? It's because the formation of ettringite monocarbonate is thermodynamically more stable than the presence of monosulfate and calcite. So, provided it has sufficient time and sufficient water, our system will always move to this side. And I plotted here the volume fraction of these phases. I plotted here 3 monosulfate, 2 calcite, and converted it to ettringite and 2 monocarbonate. And you can see you have a volume difference, actually 23%, and this volume difference can be beneficial. Because, as I will show you in a minute, the compressive strength of a cement is closely related to the porosity or reverse to the volume of the hydrated slurry. First of all, I want to demonstrate that what we predict by thermodynamic modeling also has some connection to reality. This is a XRD, X-ray diffraction of a cement which basically contained very little carbonate. And what we see here, we mainly see ettringite and monosulfate, which agrees with what we predict. We can do the same kind of exercise with the cement which contains 4% limestone. That's actually the cement you nowadays will buy in the shop or by your local provider. And there you see ettringite and monocarbonate. So we see by completely independent method, experimentally, it has a reality what we predict by thermodynamic modeling. Because as said before, we can model anything. That's not the problem, but it has to have some connection to reality. You've seen this picture before, a similar picture before this morning by Thomas. We have this maximum here calculated in volume, and this relates to a maximum within compressive strength. Most of this data are actually by Duncan Herford, who sits there up front. And we can even increase this effect. For instance, if we mix together OPC and fly ash. Fly ash, it contains also a lot of aluminium, so it has the possibility to increase this effect, and we can see that experimentally, where we have compressive strength data for 28 days, and you see the ternary mixture of limestone, OPC, and fly ash can have very good compressive strength, and in addition, it's a good deal for industry. If we stay with fly ash a bit, I said before, it's aluminium rich, it has this amorphous structure. It will have, after 28 or 90 days, a very good compressive strength. If you look on early compressive strength, it's not so great. So you have to do something about it. But on the other hand, it also produces less heat. And that's shown this morning by Thomas. It can be a big advantage if you're building big pieces of concrete out of it. Then we also can try to figure out what happens if we add fly ash to our OPC. Again, I show here a picture from modeling. This is OPC reaction as a function of time in a log scale. We produce mainly CSH, we produce some ethylene monocarbonate, and we produce or we consume some of the Portlandite. And when you look down here, you can see actually we assumed that very little fly ash has reacted. And as I said before, this is where our trouble starts. Because what we easily can follow, for instance, is the amount of Portlandite present in the system. And you see if you have fly ash, we have less Portlandite present. So that works fine. But then to know how much fly ash has really reacted, that's difficult. Because to get back from this small difference in Portlandite to a reaction degree of fly ash, you can imagine what big error you produce if you do that. Another way to do it is actually to use image analysis. And this picture is from Florian Deschner, who's sitting somewhere in the back. And basically, you can make SEM pictures. You can adapt or add a number of filters. And then finally, you get a picture like that, where you just have the fly ash out. And you can use that for quantification. You also get a reasonable result in many cases. But in some cases, it also doesn't work. For instance, if your fly ash is too small, then you just don't catch it. So there's a number of methods, and all this, there's a number of methods that you can apply. They're all quite time-consuming. They are not easy to apply. And one of the things we also did within Nanocem, and outside Nanocem actually, we tried to investigate different methods on how to assess that, and to make progress and to bring these methods to a level where also non-expert or not just PhD students can use it. One also can look at the structure of the CSH by making 10 pictures, for instance. That's 10 pictures of John Wasson, who's a PhD student at the moment with EPFL. And this is the structure, how you see it in the transmission electron microscope in a Portland cement which has hydrated for 5 years. You can see here the CSH fibrils, or we think it's CSH fibrils. And if you have the same Portland cement but add 30% of fly ash to it, the structure looks somewhat different. And the people who are much more expert in that than me, they call that foil-like fibrils. And so you see, depending on the presence of STMs, you can have quite a different structure also on a very micro or nano level, however you want to call that. I want to change topic again. I will speak about the effect of silica fume. Silica fume is basically just contains silica or SiO2, not much else. If we calculate what happens if we blend the cement with increasing quantities of silica fume, we predict first that we decrease the amount of Portlandite, similar as we did for the fly ash. We also predict some changes in the aluminium phases, and we predict also a change in pH. Now, silica fume is also very difficult to measure because we cannot see it with the microscope, it's way too fine. We cannot see it by XRD because it's amorphous. But actually, we have quite a nice possibility to see it, that silica NMR, it's not the HNMR. Peter MacDonald has shown this morning, but it's silica NMR, and this is the plot of the anhydrous phases and the CSH, and this is the silica fume. So we can use this method to follow the reaction as a function of time. Oh yes, I labeled it here, and we can follow the reaction as a function of time, and we see after 3 months most of our silica fume has reacted. And we also can realize that the presence of the SCM affects the reactivity of the Portland cement. In red, you have the cement, and in green, you have the cement plus SCMs, and you see the presence of SCMs accelerate both A-light and B-light reaction. It's one of the big questions which we don't understand completely yet. Why do we have this acceleration? A part of the answer is, yes, we have some additional surfaces where the CSH can nucleate, but another part of the answer, I think, we'll still need a number of PhD students to think about it. And the other thing we also can realize if we go more in detail is the presence of SCMs affects the composition of the CSH. It changes the calcium to silica ratio, but it also changes how much aluminium we have in the CSH. So our system, the more we go into depth, the more complicated it gets. And the more research we will need, which is good for us. This is a picture I got from Karen's and Peter's students. It's about the HNMR and about the influence of SCMs on the water distribution. In gray, you see the values. It's again as a function of time. You see you decrease the capillary water, you increase the water bound by CSH. And in gray is the data for Portland cement. In the colors is the influence if you have silica fume present. And you see you change the whole water composition just by having 10% of silica fume present. You actually have, according to Abno's data, you have less scale of interlaying water, you have more capillary water. So this instrument Peter has shown this morning offers us a completely new way to look into the structure of the CSH. I come to slag. Slag is a bit more reactive than fly ash. You get reasonable strength development. And again, you change the CSH. This is a picture from the thesis of Vanessa Kopova. And this is the same picture. You see unhydrated. You see the Portland cement, some unhydrated grains. You see hydration products. And here is the same cement with slag particles. You see here the slag particles. You still can see the presence of CSH. You can see the presence of CH. And actually, they don't look that different in this case. If you go to 10 pictures for these phases, you can see in both cases fibrils. There's some differences, but sort of difficult to capture. Karen is laughing at me because she could explain that much better than I could. If you go into more detail, you see the presence of slag in this case. It affects the composition of the CSH. This is CSH related to an OPC. On the right-hand hand, we have CSH in a system which also contains STMs. And you see, for instance, you change the calcium to silica ratio in this CSH. In addition, which you cannot see here, you also increase the amount of aluminium in the CSH. So although they didn't look too different in the picture we've just seen before, if we look from it on a chemical level, we clearly have a different CSH. And in all cases, and that's actually very, very interesting for us, we still have Portlandite present. So from the chemical point of view, they shouldn't be so different as they are in fact. And at the moment, we think that the kinetic has a lot to do why we see these changes in the CSH. You see, the SCMs, they also affect the pore structure. That's an example from a thesis done in DTU and in Denmark and in Norway. And you can see this is a MIP picture, mercury intrusion porosity picture. And depending on the amount of the kind of SCM present, you change the pore structure. And then the presence of STM also affects durability. This is a sulfate test. Basically, sulfate tests, they work very simple. You make a bar, you put it in the sodium sulfate solution, and then you measure expansion as a function of time. One can discuss how correct that is, but in any case, what you can see, this is Portland cement. This expands very fast. It actually falls apart within a few months. If you add a proper amount of slag and the right amount of sulfate in the whole mix, you can have prison that will not fall apart for many years. So the SCM's presence of STM can really change anything. Yes, and here you see the nice slag prisons. So to summarize, what is the effect of SCMs? They react slowly to Portland cement in most cases. They can accelerate or also retard the reaction of Portland cements. They affect strength. They modify the cement composition, the microstructure, the porosity, the water distribution, and they can enhance durability. Now, this is all known now, but I think we should go further, because if we don't understand what's going on, we'll never really make progress. And I want to show you some glimpse of things we are actually doing. I said before that the STMs, that they change the CSH composition. And we have at the moment 4 projects which just aim to understand what's happening on the CSH on a very simple level. We mostly work on synthetic systems. And this is the aluminium in a CSH, depending on the amount of dissolved aluminium. And you can see there's quite clearly a correlation between that. And eventually we reach a plateau, because we cannot increase the aluminium concentration very much anymore, because we start to precipitate other phases. We also can have, or we can use molecular modeling. This is data from Luis Pegado, who also sits in the audience. We can use molecular modeling to understand where does an aluminium go into our CSH. And what we predict, actually, that the CSH is very happy if the aluminium sits in a bridging position, or like here, or in a cross bridging position, and it doesn't like to sit in a pairing position. And this agrees very well with the experimental data. Or one can use NMR to understand which different environments an aluminium is sitting in. This is an environment where it's sitting which corresponds to this bridging position, but there are also other environments. This is actually an environment where an aluminium is next to a calcium hydroxide. So it's also called third aluminate hydrate. And this whole population changes as a function of composition. So the system starts to get quite complicated, and where we aim to is to implement this complexity into a thermodynamic model, and to understand what is going on, and to be able to predict where the aluminium will sit and how much we take up. Also in the case where we have different STMs. Now, if we think a bit further to the future, I spoke a lot about fly ash and slags and silica fume, and actually this is quite well known what's happening, or we know it quite well by now. But in the future, we will have to continue to face or to work towards the reduction of CO2 emissions. We also will face the development of very new cementitious materials, like they already nowadays they do. You can read a lot about calcium sulfoaluminate cement, you can read about selightment, but I'm very convinced in the future there will be much more coming with different chemicals, and there we not just can use our previous experiences to understand what's going on. We also have to look on the interaction with the environment, especially, for instance, in Switzerland, where we have our many tunnels. This is a very expensive topic if we don't understand what we are doing. And I'm sure there are much more points towards that. In the past, a lot of things was done by trial and error, and I think we need a more generic approach. We need to understand the effects on a fundamental level, not only based on chemistry, but also based on the kinetics, on the effect of microstructure, on durability. So, as I'm nearly the last speaker now for Nanocem, I also tried to quantify or to put down how Nanocem contributed to that. I think we obtained a better understanding on the role of STMs on the cement hydration during the last 10 years. And Nanocem contributed to that not only by financing some of the projects, but even much more, I think it created the environment where we could easily meet other people, where we could do networking, where we could informally exchange some ideas, which were not always that great in the beginning, but maybe were better later on. And yes, that's what I wanted to say. And last, I had only a small part of the slides were my slides. I borrowed them from many people sitting here in the audience who did work for Nanocem during the last years. So I have a big list of thank you. And thank you all for listening.